Hola amigos, now let's continue with equation of motion of our sixth chapter elements of airplane performance, page number 392. And here we see that we are considering the motion of airplane in two-dimensional plane. We are not considering the three-dimensional motion, that is the banking of airplane. That let's say this is an airplane and we are just considering its motion in two-dimensional plane like this. We are not considering vertical motion in the depth of this plane. Okay, now we will see these reference lines we have used for our convenience to make these forces, lift, drag, thrust and weight forces, which are primary forces which are governing the motion of this airplane, and we are using these reference lines to make these forces either align in the direction of the flight or make them parallel to the direction of the flight. Let's say the airplane is moving in a curvilinear motion like a circle or a parabola, and then we see that aircraft at an instant in that curvilinear path, we see the aircraft, it is that movement, at that moment we are seeing that it is pointing in this direction, the velocity is pointing in this direction, it was moving in this direction. And we know from aerodynamics that lift force is acting on the airplane perpendicular to the flight path. This direction of velocity of the aircraft is the flight path which it was following, and the forces acting perpendicular to the velocity or the flight path are termed as lifting forces, and forces which are in the direction of velocity or say opposite to the direction of velocity are drag, which are creating a resistance for this airplane. And these two are aerodynamic forces, and the force which is moving it forward is the thrust force, and we are representing over here with t over here, and it is at an angle alpha t from the flight path angle, and the velocity or the flight path which the aircraft is following is at an angle theta, flight path angle, from the horizontal. And this alpha is the angle between the chord line of the wing which is taken from here, and alpha is measured from the flight path angle, from the flight path direction to the chord line. And chord line is the line from the forwardmost point of the airfoil to the backwardmost point of this airfoil. The forwardmost point, when looked from the edge, is termed as leading edge, and the backwardmost point of the wing when looked from the edge is termed as trailing edge. And when this leading edge and trailing edge is joined, we will see a chord line, and this chord line makes an angle alpha with the velocity with which the aircraft is flying in the direction theta. And the forces over here are resolved along the flight path and perpendicular to flight path. It is very important to note that forces are always resolved along the flight path in the direction of velocity and perpendicular to the flight path. So here the forces parallel to the flight path are thrust force component in the direction of velocity, t cos alpha t, minus drag because it's opposite to the velocity direction, and minus w sine theta, this is theta, and w sine theta is this component opposite to the direction of velocity. And since here we are considering an accelerated or say curvilinear motion, we have this ma, and at a particular instant or moment of time, instantaneous velocity is given by instantaneous rate of change of velocity is given by dv by dt, and dv by dt is nothing but acceleration. So f equals ma is nothing but the Newton's law. Similarly, we have the force is perpendicular to the flight path. So forces perpendicular to the flight path are t sine alpha t perpendicular to velocity v is t sine alpha t plus L lift force minus w cos theta w, and if we extend this we will see the w will be in this direction which is minus w cos theta, and it is equal to mv square by r. Since this force is centripetal force and this force is centrifugal force, they will balance each other at this moment. Okay, now let's say we have a level flight, that is v is in the direction of horizontal plane or say horizontal direction, where theta will be equal to 0, and say that the airplane is flying steadily or say it is unaccelerated flight, which means this right hand side acceleration part will be 0 in both these equations. So since we have level flight and unaccelerated flight, we will see when we put theta equals to 0 in both these equations and these RHS terms are 0, right hand terms are 0, this equation t cos alpha t minus d will be equal to 0, which means t cos alpha t equal to d, and here t sin alpha t plus L will be equal to w because this is equal to 0. And let's say alpha t tends to 0, which means this thrust line t is in the direction of velocity v, then if we put this alpha t which is tending to 0 in these two equations, we will see cos alpha t will tend to 1, which means t is approximately equal to d, thrust is approximately equal to drag, and L plus t sin alpha t as alpha t tends to 0 will be 0, which means L will be equals to 0, w, which means for a level flight and unaccelerated flight with thrust line in the direction of velocity, we have thrust equal to drag and lift equal to weight. Let's say the aircraft was accelerating in this direction, in the velocity direction. We have now steady flight, and with that we have level flight now, and which means theta is in the horizontal plane with 0 degree, and this means aircraft is now flying a level flight steadily following Newton's second law with thrust equal to drag force and lift equal to weight. And here for this airplane, thrust is in forward direction, drag in the opposite direction, lift in vertical direction, and weight in the opposite downward direction. Okay, so this condition of level and unaccelerated flight is known as cruise condition. Cruise flight it is known. And we will see that thrust required is equal to the drag acting on the airplane. Let's say the airplane is moving steadily, so the steady force that is required to overcome drag is the thrust force only. So the minimum force that is required to overcome drag is thrust that is required to overcome this drag. So the thrust force we can say is equal to the should be at least equal to the drag force to keep it steadily moving in the flight, cruise flight. And we know thrust required equals drag, and drag is equals to q infinity s times cd. Q infinity is half rho v square, we know it from aerodynamics, half rho v square s cd. Cd is coefficient of drag, total coefficient of drag acting on the airplane. And with this drag and velocity v, we will see as the airplane moves with some velocity steadily in the flight, and as the velocity with different velocities, because drag is half rho v square, it will show a parabolic nature with the velocity. Or say thrust required varies with velocity with a parabolic variation. And here we will see that thrust required reaches up to a minimum value and again it increases. So this minimum value, thrust required minimum value, is used for airplane design to have efficient airplane performance, and for that a pilot needs to know what velocity it should be flying. And for this thrust required minimum, we have velocity at thrust required minimum. We will see this in next lecture. And last thing I would like to point out that for this thrust required minimum and the velocity at thrust required minimum is a design point of the airplane performance at which lift to drag ratio is maximum for the airplane, and we will see it in detail in the next lecture. Thank you.